Good afternoon, everybody from Italy. Hope everybody is well. Going to go through a little presentation about a digital twin that we currently are working on. So I'm working in Salvagnini, Italy. We are a company that manufactures machine tool. Okay, perfect. Okay, good. Yeah, so we are a company based in Italy. We work globally with mainly automation and how should I say, quite complicated machines, like I said, for sheet metal business. So if you think about Samsung refrigerators, if you think about General Electrics, if you think about the big HVAC companies making the HVAC equipment, usually there is a Salvagnini machine that makes at least the skin of it. So if you have an Electrolux refrigerator or a Samsung or an LG at home, probably it has been made on one of our machines. We have 37 offices around the world, North America, South America, Europe, Asia, Africa, and so on and so forth. So we are quite globally represented. So what we started to think about, because of course we as a machine tool maker has to make sure that we are always, let me say, in the front of technology. And the front of the technology now is no longer on the mechanical side, but it's on the digital side. So our R&D for sure has been switched around from, let me say, mechanical inventions to digital inventions and upgrades to track the machine's movements, to track their health, to track a lot of things. But we didn't have, or we had something. We have actually we had already a software called OPS, or Order Processing System, that had the ability to somehow sequence and optimize the flow of the Salvagnini machine itself. But if we look at the factory normally, the Salvagnini portion of the factory, the output portion is probably around 15–20%. The rest is made in other types of machines or the assembly lines or something else. So what we did was that we wanted to widen the horizon a little bit and take all our experience that we have through now, what is it, 50 years in this kind of business. We actually put together the first digitalized sequencer for sheet metal machines in 1983. It was at that point on the old DOS machines, of course, but so we have been doing it for quite a while. So we were saying, okay, so we want to do something where we can widen this 20% that we have of the total output of the factory itself. So of course we had to step out of our own environment to step into something else, like I said before, the assembly lines or the other type of equipment. So how can we do that? How could we possibly be able to gather the data to be able to try to predict the future? What we did was that we started to think in some different aspects. We read a lot about the digital twins. We did a lot of researches. We had experts here that we were discussing with, and so on and so forth. But at the end, after 2 months or 3 months worth of work, trying to dig deep into the digital twin concept, we actually took everything and threw it in the wastebasket because it became so complicated. So there was no way any of our current customer base could supply the level of data that our advisors thought that would be necessary. I mean, they have a lot of data, but it's not structured or it's not in the format that we needed. Some data are missing, and so on and so forth. So actually, we sat down by ourselves and said, okay, why do we need to make it this complicated? Will we get more gain in terms of throughput and payback if we complicate it and only 10% of our customers can use it? Or will we get an acceptable, let me say, throughput and payback, even with a little bit simpler model that could be put together in less than a morning, 4 hours of a, let me say, a medium job shop or something like that. So that's the road we chose to go. And in the department, I have process engineers, skillful process engineers that has been working in a lot of different industrial environments. I have a couple of data scientists, which is absolutely necessary. And I have actually only one software engineer who was starting to work with me in the pilot project. So we, from a very complicated picture that I'm not even going to show you, we came down to this, right? So we have a physical entity, we have a digital entity, and we have a data repository. Somehow we need to have the connectivity, number one, between the digital entity and the data repository, and the physical entity and the data repository, where we are supposed to aggregate the data and make the work a lot smarter than it was before. So this was our slogan at that point: make it simple, but make it significant, right? So you get a lot of significant result also with a simple approach. So, for instance, everything that we are running in the FlexSim on the FlexSim side, of course, we are making also normal simulations of our machines and so on and so forth, where we use a very nice graphic and all that stuff. But in this case, really, the graphic is not necessary. I don't need to show a picture. The only thing I need is a model that can work together with some kind of an optimization algorithm, and give the feedback to the algorithm by running different instances of the sequence that the algorithm have created. It's a little bit about almost, it's not quite reinforcement learning, but it is quite close to that approach, let's say. So you have to remember here, in this presentation, it's not about nice movies and nice pictures. It's simply about one thing, and that is to chase down the best possible way of making a production run through a manufacturing environment. So in 2019, we started this journey, and until 2021, so this year, we did only 2 pilot projects. So we chose 2 companies, both located in Sweden. So high technology, high level of automation, somewhat good structured data, not complete, but good enough, let's say. And both of them, the flow shop is actually a little bit larger company, but the job shop was a medium, almost small environment. And when we started these two, so we started up both of them at the same time. And this pilot project was only to give us some kind of understanding of what and how we could do it. So imagine now we are launching this in both companies at the same time. Of course, we need to have full support from the companies because there is a lot of stuff that we need to know. There is a lot of things that we need to have. There's a lot of information, interviews to be made to understand the problem. So these two pilot projects, of course, became quite in depth, and some of my guys were at these factories for months at a time, just to gather the information and understand what the good approach could be. So the resources we put into it from our side was process engineering, simulation specialists, and the data scientists, and the software engineer. That was either on site or here in the office in Italy. And then the resources from both the pilots. Of course, we had to have the operation manager, the planners, the IT, ERP specialists, the process engineers, the supervisors, and the operators. All these are a must. Right? So, because everything that we get from this group here is going to feed the information to the software engineer, let's say. The software engineer is really only a guy that is trying to, he has to be able to listen, and he has to be able to transfer the information and the stories coming from the practical people in such a way so it makes sense. And of course, here he also had the help of the process engineering and the simulation specialists. I think there is a lot of the problem today if we look at the digital twins that actually, the attempts of digital twins that are on the market today, is that we lose a little bit, when we develop, we lose a little bit anchoring to the ground. So we lose a little bit these people down here at the bottom, the supervisors and the operators, while they really are the guys that can inform us how the digital twin should work, because they are doing it basically every day, what the digital twin is supposed to mimic in the future, right? Anyhow, so this we put together. So we chose the job shop and the OEM. So it's extremes on both sides, right? So if we can cover this one and we can cover this one, we have covered everything in between. That was our strategy, basically. And this is basically our idea. So again, very simple, right? So the customer should at least have an MRP or ERP or okay, it even works with planning in spreadsheets, Excel, and so on and so forth. But it's easier for the automation side of the things if we can communicate directly with an ERP, MRP, with an XML format or some other kind of data format, JSON or whatever we choose. We call it LBIT, so it's a lean binary digit, right? So out of the bit we create the lean, basically. And then we have the workshop. So those are the three things that we need. And of course, we also need to check the quality of the data that is currently on board. Excuse me, I have a little bit of a cold, so I'm coughing a little bit, but I hope it's okay. So from this pilot now, that has been running since 2019, like I said, we had one software engineer, and we actually built from the beginning that we knew, and there is probably 5,000 hours worth of code writing in this pilot software. But from the beginning, we already knew that, okay, we are writing the software, we are trying to do it as complete as possible to really understand if we have captured everything we have. But we also knew that this would be thrown away, the whole thing would be thrown away once we were finished, because then we needed, of course, to industrialize the interface if we were going to make it like a commercial software, let's say. So what we have is, with these two pilots projects now, we are directly connected through an API. So our web server here in Italy actually hosts the FlexSim license with the possibility of self-setting up the model without anybody dragging and dropping it. We are running it without any visuals, so we don't have. It's basically like a headless application, right? So we run it black without any graphic at all, just to get a little bit more performance maybe when we have too many entities in there. And of course, also the web server here is also running all the algorithms. So what's happening in basically is that the customer starts to, he plans usually 3 or 4 days ahead, right? So once the planner is done, he does the planning in the Elbit software that you can see on, let me see if I can. So in this interface here, right? So here you have Thursday, Friday, Monday, and Tuesday is, so here in this particular case, this screenshot, there's 2 days planned, Thursday and Friday. So once what he does is not really dragging in anything or importing anything. He's just saying, okay, I want to plan for Monday the 29th. When he starts the planning by pushing the button, Elbit automatically contacts the MRP system of the customer, gets all the parts or details or units or refrigerators or whatever that is due to be starting production on that particular day. So automatically the MRP sends us the list of the units that needs to be produced. We import it, we break down the list, and we split it up, the bill of material basically. So we have all those parts, the motors, the compressors and everything. So we know exactly every detail that we need to take into account. Once we have done that, imported, once the planner has done that import, he's basically ready to start rock and roll, right? So what he does, he simply choose he's pressing the button called optimization. And in this particular example, we have 8 different algorithms that are simultaneously kicking on and taking that particular mix of production, make a sequence, let me say, optimization of how the product should be sequenced through the production based on the cycle times, based on how many operators we have, what machines are, is there any breakdown, is there anything else that could impact the sequence. When this operation we struggle with for a bit, because actually some of the algorithms took 3, 4, 5 minutes to come to a conclusion, to converge at the end. But after about 1.5 months of going through it more thoroughly, the algorithms and the architecture of the algorithms, we found ourselves somewhere around 20 seconds to run all the possible algorithms on the same sample. Because why do we have multiple algorithms? Because the mix are changing so much. So depending on what mix, they can have small units, big units, medium units, and some days they can have more medium than small. Some days they have more big than medium, and so on and so forth. So there is a lot of variation. It's a mixed model production. So therefore, we chose to implement a multiple of algorithms in this pilot just to see, okay, what strategy and how we are thinking, which one of these would has been performing the best through this pilot project. By doing that, we could understand also and investigate what was the factor that made that particular algorithm work better than the others. So this was only for the pilot project where we run multiple algorithms at the same time, let's say. So once the planner has done that, he gets the result with the graphs, and he can also, if he wants to, make a comparison. So here, this is basically the same production list, but it is 3 different algorithms that have calculated the throughput, right? So each line here, it is actually a timeline. So you have the time or units to be manufactured. And you have here on the y-axis, you have the minutes for that shows us, okay, where are we with the different stations. So each line, this is an assembly line, right? So each graph line here represents one station. So orange is one, red is one, and blue is one, and so on and so forth. So, and this is over the time. So these are the units planned for the day, and this is the time, 8 minutes. We are around 8 minutes intact for each and every one of them at the maximum. The lowest station has a much lower level of utilization, as you can see here. The gray shadow in the background, that's the takt time. We can never go above the takt time because that means that we are not able to do the demand that has been planned for the day. So here we can chase different things. We can say, okay, give me the algorithm that gave me the best make span, so the total flow time, let's say, or give me the algorithm that gives me the smoothest production. So I don't need to, if you imagine in a car, you start and you stop, you start and you stop, you stop and you stop, because you have long cycle time, short cycle time, long cycle time, short cycle time. So it goes up and down, up and down. So in this case, we can see that this particular algorithm here calculated to a very smooth flow. You can see the lines are straight, quite straight, I would say. There are a couple of bumps, but they're quite straight. While in these other two, there is a little bit more up and down. So it means that the flow becomes very erratic. So at some point you are overloaded, at some point you have nothing to do, at some point you're overloaded. So, and this is a parameter that you can set in the algorithm, actually. You can say, okay, I want the algorithm to chase 40% smoothness, but I want it to chase 60% total time, which means that the algorithm will focus most of its calculations to bring the total flow time down to the minimum possible, but still keep 40% weight on the smoothness. So I get a fast flow time, but also I get somewhat a smooth day, let's say. So anyhow, in this case, this algorithm is according to me the best, because probably it has the shortest make span, and it also have the smoothest flow. So we can actually see here, this is the same pictures. These are the graphs that we saw on the other side. And here you can see we have the KPIs right here. It's hard to see, I don't know. But you have the make span here of the algorithm in the last row. That's the KPI that we have here. We have a lot of other KPIs. We can see the standard deviation on the moving average. We have maximum tardiness. We have a lot of different KPIs that we look at. But once it's done, they simply choose the algorithm that is best. Then on the production side, of course, they get a lot of information here as well. They get particularly for what is the day's work, what is the current delay in the production. So here we are actually live following the production of the assembly line and compare it to the output from the simulation model, the flexing model, and compare what the digital twin predicted and what is the actual current situation. So this shows that the higher this curve gets, the more in delay we are because of something that's happened. So we want to try to keep this as smooth as possible. We can also see for each station how much the operator is loaded. So each single operator is also tracked with a load, and it's tracked over different times of day. So from morning to breakfast, from breakfast to lunch, from lunch to coffee, from coffee to finish in the evening. So here the supervisor is also getting advice from the software where he should put the operators, if there's any extra operators needed, and so on and so forth. Oops. So there is pretty much a complete, let me say, information source. So what we also agreed upon from the beginning, the optimization functions of Elbit should be simple, okay? So minimizing the make span, so the total throughput time for the day's work, minimizing the total weighted completion time. With the weighted completion time, you're tracking basically how much WIP do you have currently in your pipeline, right? So we want to keep that as low as possible because we want as few items as possible, but with a high speed flowing through the system, the machine, or the assembly line. And then minimizing the maximum lateness and idle state of machines. Of course, we are also tracking if we are, like I said before, if we are late, if a machine is idle a lot, or if we need to rebalance something. So now, I only have 2 minutes left. Now, what we have done since this pilot project is finished, we have actually now started to make the industrialized version of the software, right? So what we have is basically three categories in the software. Setup, which is the process engineer or the operator or the supervisor. We have the planning department, and we have the visualization and information back to the operators on the floor, which is very important. But what they can do now, basically customer themselves, they have a canvas, they can drag and drop in processors or machines, let's say, or assembly stations. And then based on the data input we get, the software will automatically create by itself if there is a buffer before, if there is a buffer after, which is this machine connected to, or this assembly station connected to the next station. All that is coming from the import data. So by being a little bit smart and calculating or looking through the data that we import for the model, we can also determine the topography of the model. So basically, what the operator needs to do is to drag and drop in the different stations or machines, and then give them an attribute, how they work. There are certain predetermined attributes that they need to set. And then based on the data output, the automatic model building is done in the server here in Italy, and the model is ready to be used. They also set up the normal work schedule. So they make the factory configuration with the canvas. And let me just go forward here a little bit. And of all this, a very simple model is run, but nobody sees it, is run on the server here in Italy. So the graphic is not, like I said before, used at all. Based on the output from this model, the server sends back the information to the user, where he now can look at the results in the graphs and the curves that I showed you before. What we have done now, the last thing we did was we said even this is too complicated for a user that has never used a simulation before. So we want somebody to be able to go in and say, okay, I want to check something. So I want to build a model in 2 hours with all the attributes. And then I want to run through a production sample in those 2 hours. I might not be exact in my output, but I should be within 90% correct at least. So actually now we removed everything except one component, and that is the station or the machine itself, which now, so the user is just clicking this and saying, okay, I drag this here, and once he does that, he gets an attribute list about that machine on the side, and he sets the attributes, how many operators, how does it work, there are certain criteria that he has to fill in. And then when he imports the data, all the connections are made automatically, and it is also determined if it's what we call a main machine or a sub-machine. In this case, this has with the strategy to do. But based on this, he can now build his model, like I said before, in 2-3 hours, and then extract data from it daily, use it as a planning tool, get the optimized solution together with the algorithms, all remotely on our web server, connected to an API with his MRP system. So that's where we are currently today. And we are now continuing to develop the visualization for both the operators and the supervisors and the operation managers. Each one of them should be able to have the data available on their smartphone or on their tablet or on their computer in the shop. And of course, at the line, each operator then has their own screen that shows them exactly where they are supposed to be at that minute, which order they should process, and so on and so forth. So they are also seeing, am I late or am I in front? Do I need to do something? Do I need to call another operator or make some other decisions? So that's where we are right now. This was kind of a compressed presentation. Sorry to drag over a couple of minutes.
Well, not a problem, Ricky. Thank you so much. I do know we had a question come in already, but we probably do need to move on.
Yeah.
Would you be able to maybe answer that question? And then if you wouldn't mind, we'll have a 15-minute break after this session.
Yes.
If you wouldn't mind maybe speaking to some people in the lobby if anyone has additional questions.
Sure.
Perfect. So yeah, just take those in the summit lobby during the break. And
okay.
Excellent. Thank you very much.
Thank you.